Hey guys, Buildzoid here, and today we're going to be taking a look at the most, I think this is MSI's cheapest AM4 motherboard, the B350M Gaming Pro. And if you remember MSI, if you remember AM3 Plus motherboards, especially the low-end ones and even some of the mid-range ones, and especially from MSI, you'd probably automatically think this has to be a freaking fire hazard, because to be completely honest with you, that's exactly what the AM3 Plus boards from MSI were. You didn't even really need an FX 9590. If you just overclocked an FX 8350 a little bit, you could very easily send the VRM, well, not send it. The VRM would just go up in flames for you. So, that is very much the question here. Is this low-end motherboard just as bad as all the AM3 Plus ones were? Will it not survive a Ryzen 8 core? Well, I will tell you, and I'm not going to tell you right now, because first of all, we need to go through all the different VRMs, and then we'll get into the actual current capabilities. So first things first, here we have the V-Core VRM, and that's the one that, this is the one most important for core overclocking. Well, actually, for overclocking, just core clock is the main clock you're going to be working with. This is the most important VRM for that. I recommend about 1.42 volts. Actually, no. AMD recommends up to 1.425 volts for overclocking Ryzen CPUs. So 1.42 volts is what I do my VRM ratings at. 1.42 volts should be enough to hit anything from 3.8 to 4.1 gigahertz on all of the Ryzen CPUs. Depends on luck of the draw, on your luck with the Silicon Lottery on what you actually end up with, but this is the maximum safe voltage. So yeah, then for the SoC VRM, we have it up here. It is rather oddly laid out in terms of it's not a layout you see very often, but in terms of actual design, it makes quite a lot of sense. Because basically the power plane ends up being between the two chokes instead of just in front of the two chokes, which, if you had more chokes here, then that's what you'd end up with. You'd have a power plane like that. But, yeah, so that's the SoC VRM. That's most important for memory overclocking, but the voltage this controls affects memory overclocking. The VRM itself, I've not seen a motherboard where I would say that it would actually, like the SoC VRM design, would actually affect your memory overclocking capabilities. You'd probably get affected more by like BIOS programming, memory trace layout, or even memory power. And even there, I really doubt it, because both the SoC and the memory memory power consumption is just really low. DDR4 does not need a lot of power. The SoC does not need a lot of power, and so you don't really need ridiculous overkill VRMs to get good overclocking in the memory in terms of memory overclocking. So, yeah. Those are all your different VRMs. For SoC, maximum voltage, I'd recommend 1.2 volts. Memory, AMD says up to 1.5. I personally tend to stick to about 1.45. I'm willing to believe them that 1.5 is fine for Ryzen memory controllers. And even for the memory sticks, because DDR4 memory sticks, the only ones that I've heard apparently died were well above 1.8 volts. It wasn't even like 1.6 or something. It was just way above 1.8. So, yeah. That's that. So now let's actually take a look at the VRMs in more detail. So all the VRMs on this motherboard are using the exact same Mosfets in the exact same setup. We're looking at 2 high side FETs, right, and 2 low side FETs per phase everywhere. So those are 2 high side FETs again, and those are your 2 low side FETs. And then here you have 2 high side FETs and 2 low side FETs. And this is, yeah, every one of the big VRMs on this board does that. The actual Mosfets themselves, for your high side, you're looking at Nyko Semiconductor, Nyko PK616BA Mosfets, and for your low side, MSI, for the low side, MSI is using the Nyko PKP, not R, 632BA. These are very much budget MOSFETs. I'm not sure how cheap they are. You basically can't, you can't even get them at most parts suppliers at all. You can find them on AliExpress for less than, I think it was less than $0.8 a piece in 5-piece batches. And if that is comparable to what you normally get, if that has the same kind of discount that normal transition to bulk purchasing goes, then these things should be less than $0.50 a piece. And MSI obviously is probably buying directly from the manufacturer, so these things are extremely cheap as far as MOSFETs go. Because you can also get MOSFETs that cost well over, you can get VRM components that cost $3 a piece, Admittedly, they also do a lot more current, and they're more efficient, and just generally better than what you have here. And MSI also happens to be using these PK616 and 632 MOSFETs on every single motherboard on AM4+. So I'm kind of not impressed with them using them on the more high-end boards. Not that that's really a problem, because AM4 AM4 doesn't use that much power, but honestly, I would expect the higher end motherboards to get better VRM components. I mean, come on, is that too much to ask? Could you not use the same cheapo MOSFETs on everything? But yeah, so these are the MOSFETs used across the board. What does that mean for your actual power capabilities? Before we get to the power capabilities, yes, I'm going to make you sit here a while. We're going to go over the control scheme. So the controller is for both the vCore and the SoC is this chip right here, and that is an RT8894 from Richtech. This is a 4+2 phase voltage controller that MSI is using on a ton of their AM4 motherboards. I'm not entirely sure if it is used on also all the way up to X370. Well, I know the X-Power uses a different voltage controller, but I'm not sure how many of the boards MSI does use this controller. I know most of the B350 boards that are 4+2 phases use the RT8894. This uses the RT8894. And then once you go sort of past the 6 phases and up phased, if the board has more than 6 phases, it probably isn't using the RT8894, because you can't double off of this voltage controller, because it does integrate the gate drive. And integrated gate drive basically means you can't double, because the controller directly controls, in this case, 3 of your phases. So you can't actually put a doubler between the controller and the phases. So, you need a different controller for anything more than 4 phases with this, for anything more than 4 phases. So, yeah, right here, the motherboard is running in 3+2 phase mode, and the voltage controller goes all the way up to 500 kilohertz switching frequency. Unfortunately, I don't know where it starts, because the datasheet, well, I mean, it probably says it somewhere. I just couldn't be bothered finding it. But it does max out at 500 kilohertz. It won't go beyond that. It internally limits itself to that frequency. I, of course, do all my power ratings at 300 kilohertz because that's sort of a sweet spot for efficiency and voltage regulation. So, yeah, the VRM right here is running in 3+2, and we're looking at 1, 2, 3 phases like that. And then, of course, 1, 2 up here. Honestly, I think a 3-phase to a 4-phase, that's a big enough difference in phase count that you might actually see a improvement in overclocking for a given voltage just because of the extra phase and the better voltage regulation that brings to the table. So, and in terms of actually seeing better overclocking, I think you'd see probably like 25, maybe 50 megahertz. In extreme cases, it might go all the way up to 100 megahertz, but that I think would also depend on how the capacitor bank, like what kind of capacitors well, how much capacitance the VRM also has and what kind of capacitor selection was made on the motherboard, because just the phases alone don't do don't do all the voltage regulation work. The capacitor banks play a huge role in that as well, which is why you have capacitors right under the CPU. And then actually, if you took the lid off of a CPU, if you delidded a CPU, you would notice that there are more capacitor banks on the CPU itself. There's, you know, there's capacitors everywhere to try get more flat voltage. That's really the goal of any VRM, produce a flat voltage at varying current load. And the better you can do that, the better your VRM is, assuming that it also can handle very high current. That's the other criteria. So 3-phase is not that great at holding a flat line, but it shouldn't actually blow up if you were to run a Ryzen 8 core, as assuming 1.42 volts, 300 kilohertz switching frequency, and 125 degrees centigrade operating temperature, this VRM is capable of doing, well, 125 degrees operating temperature, 300 kilohertz, 1.42 volts. You're looking at 100 amps producing 21 watts of heat. Well, actually, no, 22 watts. Misread my notes. 22 watts of heat, just like losses, which is quite a lot, especially considering that the heatsink on this motherboard is kind of anemic. But you shouldn't really have a, like, it should be doable as long as you get decent airflow over the heatsink. And to that extent, I'd actually recommend that if you're buying like a Ryzen 8 core and you're gonna if you have a budget that you're balancing between your motherboard and your CPU cooler, and you're forced to buy this motherboard because your CPU cooler costs a lot of money, and by that I mean you go and buy like $100 or $100+ AIO, throw the $100 AIO right out and go get a better motherboard. Because you can get, like, a better motherboard should clock better than this. If, like, you're gonna hit the motherboard limit before you hit the cooler limit, in my opinion, if you go for this board and then spend a lot of money on a cooler. Now, if you're already very budget limited and you're, like, budget limited on your cooler and on your motherboard, then yeah, this should be fine. If you're only aiming to hit about 3.8 gigahertz on an 8 core, this VRM will work fine. If you're on a 6 core, even 4 gigahertz is doable because it's 70 amps. This VRM should only throw off about 11 watts of heat. So that's actually, you know, that's not going to be a problem even for the tiny little heatsink that this comes with. But if you're looking to run 4 gigahertz, 1.42 volts on an 8 core, I'd honestly recommend just get a better motherboard because, you know, this kind of sucks. Now, if you're wondering about absolute maximum rating, because this is just sort of typical load, depending on what kind of overclock and which CPU you're running, theoretical maximum rating is 222 amps on this, which makes this look way better than, say, like the ASRock 3+3-phase VRM design that we looked at last time. The thing is, the way my calculator does VRM calculations is I tell it what voltage I want, I tell it what temperature the VRM is going to be at, and what switching frequency I want. The calculator then assumes that no matter how much current goes through the VRM, I am able to maintain that 125 degrees centigrade temperature. You're not going to do that if you try to push anything beyond... you're not going to manage that if you're trying to push 222 amps. Because 222 amps through this VRM is going to kick off 90 watts of heat. That's uncoolable. That is literally uncoolable. And interestingly enough, if you try to do 150 amps, it'll kick off 45 watts of heat. Which I'm going to say is still not realistic for the heatsink that this motherboard comes with. Now, if you were to put a water block over the VRM, which is completely stupid, because that would cost a hell of a lot more money than just buying a better motherboard, yeah, you could actually run 150 amps through the VRM. But as I said, buying a water block to run 150 amps through this crapshoot of a VRM is the dumbest thing that, you know, somebody has come up with in a long time. Because you could just go and not buy a water block and buy a better freaking motherboard. So, yeah. that's my opinion on that, as well as sort of the calculations. Interestingly enough, this motherboard does have one of the highest theoretical current limits that I've seen of the motherboards that I've sort of just quickly pre-checked, just because, well, MSI uses these Mosfets everywhere, and I can change the number of Mosfets in the VRM really, really easily. But at 150 amps, this VRM gets the same amount of heat output as basically every other VRM in this price range. So this one doesn't have a significant advantage because of that maximum rating, because at 150 amps, it still throws off the same 45 watts of heat that almost everything else does. So, and at 100 amps, it's the same efficiency, and at 70 amps, it's actually, I think this one actually starts losing once you really get the current draw lower and lower and lower. So, this VRM, you know, it'll work. For a 6-core, it's actually perfectly fine. For an 8-core, I recommend you go get something better. If you really, really want to push your CPU, go just get a better motherboard, because this thing is terrible if you plan to exceed 100 amps. So that's that for the V-core. Now let's move on to the SoC VRM. The SoC VRM here, it is a 2-phase, same MOSFETs, high side, low side, assuming same testing parameters, so 125 degrees, 300 kilohertz, except that 1.2 volts instead of 1.42 volts. You're going to be looking at about 30 amps of current consumption through the VRM, and that'll produce about 4 watts of heat. This is less efficient than some competing, like 3-phase or 4, like this is less efficient than other VRMs, but the SoC VR, like, it's 4 watts. It's really not anything I would worry about. Really, the big focus, I'd say, is this 22 watts of power consumption at 100 amps. If you get a better motherboard, like, say, the ASRock Tai-Chi, which is a lot more expensive, but that motherboard actually puts out only, like, 11 watts of heat for 100 amps. So you literally save 11 watts by just changing motherboards. And then if you were to go, you know, there's other cheaper boards. Most other boards are sort of between, like, there's a lot of motherboards that go below this 22 watt figure once you start moving up the price stack a bit higher. So, yeah. The V-Core VRM, you can save a decent amount of power. The SoC VRM, the lowest, I think, is like 1 watt on the SoC VRM, which at that point, your driver losses and all the other losses that the VRM incurs are going to be are probably going to dictate power loss more than the actual conduction and switching losses through the MOSFETs themselves. Now then, the memory VR. Oh, well, maximum theoretical throughput on the SoC VRM here is also 152 amps, but that's at 62 watts. So unrealistic, and you can basically ignore that. Unless you plan to somehow zip tie a water block onto these MOSFETs. But again, you know, I said that's dumb on the V-Core, that's dumb on the SoC. And the SoC really doesn't need to deliver that much power to a Ryzen 7 8-core or a 6-core or a 4-core. Because it only powers the SoC, which is the memory controller, some USB, some PCIe, and some SATA connections. And they don't really pull that much power. In my testing, it works out to about 30 amps with 3200 megahertz memory. So, you know, I can't see it getting, I can't see you needing more power on the SoC VRM. Now then, moving on to the memory VRM, the very last one here, same MOSFETs again, lower maximum current limit. We're looking at like 80 amps, 30 watts or something like that. It doesn't really matter. This is a DDR4 motherboard. Yeah, well, this is Ryzen runs DDR4. This is a 2-DIMM board, so your maximum current consumption should be about 5 amps at 1.45 volts. And at that kind of current draw, you're looking at maybe 1 watt of heat output on the memory VRM, which really that's negligible. And even if you had like a 4-DIMM board, which this VRM gets recycled a lot, this single phase, like MSI uses it a lot for their other motherboards. On other motherboards, you'd be looking at like 10 amps for your DRAM. And there you'd see like 2 watts of heat output, which again is just completely negligible. That's nothing to worry about. So, you know, that's not a problem. That pretty much wraps it up. So, will this motherboard work in a pinch? Yes. Would I recommend that you buy this motherboard if you want to overclock? Not really. You know, you can get a 4-phase for a little bit more. You can get significantly. Between like at around $150, you can get some really nice VRMs on your motherboard, like way better than what you get here. And yeah, but if you're so for an 8-core, I'd honestly recommend, you know, spending extra money on your motherboard. But if you're going for a 6-core, this really isn't this isn't too bad as far as options go. 11 watts of heat at 70 amps through the V-core VRM really isn't that much. So your VRM won't be, you know, at imminent danger of burning out. And you should be able to max out a 6-core CPU on this. But I'd still say, you know, a 4-phase board might still be able to actually overclock a bit higher for a given voltage. But yeah, in a pinch, this'll do. There's nothing this is not like AM3 Plus, where motherboards in this price segment would literally burn out the moment you tried to go past sort of 4.4 gigahertz. So yeah, you know, that's sort of my verdict on it. I mean, if you're desperate, this will work. If you're not desperate, I recommend go get something better. If you're running an 8-core, I'd honestly say it's best if you just keep it around 3.8 gigahertz. You could probably push all the way to 4, but that VRM heatsink is kind of anemic, and if you do get good airflow over it, it should probably manage to dissipate 22 watts, especially if the VRM hits 125 degrees. But, you know, your capacitors won't really appreciate that, because while MOSFETs are fine all the way up to, well, they're not technically fine all the way up to 150 degrees. But if any MOSFET goes above 150, it'll die instantly. That's pretty much how they like. You can't even store MOSFETs above 100 degrees. It literally says in the datasheets you cannot store MOSFETs above 100 degrees. But if a VRM, you know, like this VRM right here is 140 amps, 140 degrees, and these MOSFETs would still theoretically be capable of handling 100 amps. Your capacitors, on the other hand, really won't appreciate being above 100 degrees for extended periods of time. You know, capacitors are rated at like 105 degrees, and at that temperature they get a, you know, say 5,000 hours or 10,000 hours or even 12,000 hours if you look at really, really high-end motherboards. But on cheaper boards, it can go down to as much as low as 2,500 hours at 105 degrees. And really cheap capacitors, which nobody uses on motherboards these days, are as bad as like 85 degrees and 2,500 hours. So, you know, the MOSFETs might be fine at high temperatures. The rest of the VRM really won't appreciate it, and you know, better VRMs will get you a better lifespan and overall just, you know. So it'll do in a pinch. Not really a fan of it though. But yeah, for 6 cores it should be just fine. For 4 cores, knock yourself out. They're like 4-core Ryzen CPUs, you know, absolutely no issue running on this. So that's it for this video. Thank you for watching. Like, share, subscribe. Leave a comment down below if you have any questions or comments. If you would like to know how I do all my VRM stuff, there are videos down in the description. Well, there's a link to a playlist down in the description below, which does how VRMs work and how I do my MOSFET current ratings. Sometime soon I plan to add like an updated load line calibration video into there. So yeah, you know, if you're interested, you can check that out. If you would like to support what I do here at Actually Hardcore Overclocking, down in the description again, you can find a link to my Patreon and Actually Hardcore Overclocking shirts and my PayPal. So, you know, if you would like to help out, I'd really appreciate it. Thank you for watching, and see you next time.